Hello guys, in this video we're going to analyze a doubly reinforced concrete beam. So this is the cross section of the concrete beam that we have. So as we see, it is doubly reinforced. It has 3 number 9 on top and 6 number 9 at the bottom. The height of the beam is 20 inches and D prime is for the top layer of the steel rebars. It's 2.5 inches and D 16.8 inches, and DT is for the bottom layer of the steel rebar. It is 17.5 inches. So these top three tables, these are our inputs. So we manually insert all these information here. So B or BW 12 inches, H is the height of the beam, D prime, D that we have it here also, and DT. So concrete properties, FC prime is 4 psi, Fy is 60 psi for steel, and ES, modulus of elasticity of the steel rebar, 29,000 psi. And beta 1 is 0.85. 0.85 is for the FC prime, the 4 psi FC prime or 4,000 psi FC prime. And the epsilon C is the concrete strain, it is 0.003. And a steel rebar formation is prime is for the top layer. We have 3 number 9 on top, and the area of that is 3 square inches. And AS is the area of 6 number 9 at the bottom that we have is 6 square inches also. So the reason that we are using Microsoft Excel to solve this problem, because we cannot find an exact neutral axis depth or C in this, so that's why we use the iterative method to find the exact C, so the forces meet the equilibrium condition on the section. So to analyze this, we go step by step. So our step number 1, first we have to confirm that the tension steel area meets the minimum requirement, or AS min. These 6 steel rebar has to meet the minimum requirement. So this is the equation for the minimum requirement, or AS min, has to be the max of 3 square root of FC prime over Fy multiplied by BW multiplied by D, or 200 psi over Fy multiplied by BW multiplied by D. So we have to choose the maximum of these two. In our situation, the 200 psi is greater than 3 square root of the FC prime. So we go with 200 psi. So we use this part of the equation. So we change that to psi because our Fy is in psi. So I get the AS min 0.65 square 67 square inches, which is smaller than 6 square inches. So we are okay. So we meet the AS min requirement. The next step is assume that tensile steel is yielding. So assume that these 6 number 9 that we have here are yielding. So our Fs has to be equal to Fy, which is the yield strength of the steel rebar. Number 3 is select an initial value of C. So we just select the initial value for the C. It can be anything, but we know that it has to be bigger than the D prime. So some books, they choose something between D over 4 and D over 3. So D over 3 is 5.6 inches and D over 4 is 4.2 inches. So I select something in between these two, select 5 inches. So it's a trial, so we can change it anytime if you want, and we have to change it until we meet the equilibrium condition for the forces on the section. So we select 5 here. Number 4, find the strain in compression reinforcement. So you find the strain on these 3 number 9 rebars. So this is the equation for that. Epsilon S prime is equal to epsilon C multiplied by C minus D prime over C. After plug and chug all those values, so we get this value is prime is 0.0015. So Step number 5, find stress and compression reinforcement. So we find the stress on that Fc prime is equal to Es multiplied by E prime. E is the modulus of elasticity, 29,000 psi. We have it here. So after plug and check all those numbers, we get the Fs prime is equal to 43.5 psi. Just make sure that it should not exceed Fy or 60 psi. That's the limit. If the value increases from the 60 psi and decreases from the minus 60 psi, we select 60 psi or minus 60 psi. So we have to change it if it is above or below 60 and minus 60 psi. We have to write 60 over here. So the other step is, which is step number 6, find force in compression reinforcement. So that was the stress. Now we have to find the force on that. The force is CS. C sub S is equal to S prime multiplied by Fs prime minus 0.85 Fc prime. So after plug and check all these values that we already have it, we have S prime and we have Fc prime also, and we found Fs prime here. So we get the force and compression reinforcement 120 kips. So number 7, find the concrete compression forces. So we find the concrete compression force at the top layer. So the equation for that is C sub C is equal to 0.85 Fc prime multiplied by beta 1 multiplied by C multiplied by B. So we have B, we have beta 1, we have C, trial C, and we have all these values in plug and check, and we get C sub C 173 kips. Number 8, find force and tension reinforcement. So we have to find the force in these as 6 number 9s. So the equation for that is T is equal to ASFY. We have A 6 square inches and we have Fy 60. So we multiply that. So we get 360 kips. So number 9, check section equilibrium. So we have to make sure that the forces on tension and compression zone are all 0. So we have C sub C plus C sub S minus T has to be 0, or C sub C plus C sub S has to be equal to T. So after plug and check all those values, we get minus 66. So that means that our tension zone has more forces than the compression zone. So if this value is negative, we need to increase the C. If it's positive, we need to decrease the C. So it's negative, we have to increase the C. So we can do it, there are two ways now. We can run a solver to do that, or we can use iterative procedure. Iterative procedure is that we keep changing the C. For example, it is 5, I change it to 5.5. So now we still need to increase it because we still got a negative value over here. So I just want to show you how to run the solver on Microsoft Excel. So we select the cell, we go to data menu, and we go to the solver. So we set the value of to 0, and we change this value by changing this. So it's our C. So I go and change it. Then I think that I selected twice. Select it only once, and we ran the solver, and the solver found a solution. We are good. Okay. So now we see that, yeah, we meet the equilibrium condition. It's all 0, and our exact C is 6.2 inches. So we check it's all good. Right now we found the C. After finding the new C, we have to make sure that Fs prime is still in between minus 60 or 60. Yeah, we are still good. 51.86 psi is smaller than 60 psi. We are still good. If it's not good, we have to change it to 60 and rerun the solver. So number 10, we have to confirm that tensile steel is yielding. So on number second, on step second, we assume that it's yielding, but number or step 10, we have to confirm that it's yielding. So this equation for that, epsilon s is equal to epsilon c multiplied by d minus c over c. So after plug and check all those values, we get epsilon s is 0.00514 is greater than epsilon y, which is if y over e is 0.00207. Yeah, we are okay. The tension is still is yielding. 11, calculate A. A is equal to beta 1 multiplied by C. We have beta 1 and C. I can check, we get the A. Calculate the nominal moment. So this is the nominal moment equation. After plug and check all those values, we have C sub C, C sub S, D, D prime, D, A. So we get this value, Mn is 5120 kips inch. So I divided this by 12, I got the Mn 427 kips foot. So number 13, compute the strain reduction factor phi. So just make sure that if you want to find phi in this kind of problems, we have to use a dt. That's why we have the dt over here. It's from top to the middle of the bottom layer of the steel rebar on tension zone. So the equation for that is epsilon t is equal to epsilon c multiplied by dt minus c over c. So we have all these values. After plug and check, we get the epsilon t is equal to 0.00548, which is greater than 0.005. So the beam is tension controlled. So our phi is 0.9. This is a reference for these kind of problems. If you want to deep dive, you can take a look at this book. Okay, guys, thank you very much for watching. I hope it was helpful. Bye. See you next time.